So I want you to put yourself in these shoes for a second. Picture the fluorescent lighting of, like, a really sterile office.
Oh, man, I can see it already.
Right. You are a data center facilities manager, and it is 2:47 a.m. on literally the hottest night of the year in mid-August.
The absolute worst time for anything to happen.
Exactly. You're dead asleep when your phone just starts vibrating on the nightstand. It's that automated alert call you absolutely dread getting.
Yeah, the one that means your night is officially over.
Pretty much. The primary chiller on the roof has tripped offline, and you know immediately what that means. Within maybe 18 minutes, 400 server racks downstairs are going to start overheating.
Which is a complete nightmare scenario.
A total nightmare. So you are frantically pulling on your clothes, pulling up the dashboard on your laptop, and you're forced to execute an emergency protocol, a 60% computing capacity shutdown.
Just a massive hit to the system.
Massive. That single button press affects 12,000 customers across 3 different time zones. They are instantly offline. And why? Well, because the dashboard tells you there was this sudden, catastrophic, totally unpredictable mechanical break inside the main compressor.
Yeah, but see, the word unpredictable is, it's doing a lot of heavy lifting there.
Is it, though? Because it feels unpredictable in the moment.
Sure, in the moment. But when we actually look at the postmortem data of these exact types of incidents, that whole narrative of a sudden break completely falls apart.
Wait, really? It doesn't just snap?
Not at all. The machine didn't just snap at 2:47 a.m. The root cause in the specific event we are analyzing for this deep dive was actually a painfully slow refrigerant leak at the compressor discharge service valve.
A slow leak.
Yeah, a really slow leak. It had been silently releasing R134a refrigerant for 11 straight weeks.
11 weeks? Are you kidding me?
I'm completely serious. By the time that system finally tripped on a low-pressure safety switch, I mean, it had already bled out 35% of its total chemical charge. The thermodynamic warning signs were just screaming in the background the entire time. They were completely visible to the right kind of mathematical model 9 weeks before the actual failure.
9 weeks of bleeding out, so they were basically flying completely blind while the machine slowly suffocated.
Exactly.
Yeah.
Staring at a dashboard that probably showed solid green lights the whole time.
That is just wild to me. And that is exactly our mission for this deep dive today. We need to figure out how an industry full of incredibly smart engineers and, multi-million-dollar equipment ends up in a situation where they are completely blind to a catastrophic failure that takes 2 entire months to develop.
It's a huge structural gap.
It really is. So we are going to identify the primary hidden structural bottlenecks within industrial maintenance workflows. We'll pull apart the physical reality of how these machines actually destroy themselves and why the sensors we've trusted for decades are just structurally incapable of warning us in time.
Right, because the old hardware just isn't up to the task anymore.
Exactly. And we also need to map out the sheer financial absurdity of waiting for these systems to fail versus the budget required for full sensor integration.
Which is surprisingly affordable, by the way.
Yeah, we'll definitely get into that. Plus, we're going to define a very concrete 48-hour retroactive experiment, a way to prove that predictive AI can spot these invisible failures without risking a single piece of live equipment.
That's the part that really changes the game for the technical teams.
For sure. But to start, to understand why these massive, highly sophisticated facilities fail so spectacularly, we kind of have to go down to the absolute base layer of the machinery, right?
Yeah, you absolutely do. You cannot fix a maintenance workflow if you fundamentally misunderstand the physics of the machine you're maintaining.
Makes sense.
So we really need to look at what happens inside industrial screw compressors during a physical phenomenon called liquid slugging.
Liquid slugging, I've seen that term thrown around in the engineering logs, and it sounds vaguely organic, honestly, like something you'd find in a swamp.
Right, it sounds kind of gross, but in reality, it's a violently destructive kinetic event. It is the absolute nightmare scenario for an HVAC engineer.
Walk me through it. What is actually happening?
Let's build a mental model here. An industrial compressor is essentially the beating heart of a vapor compression cycle. And that cycle has 4 main stages: the evaporator, the compressor, the condenser, and the expansion valve.
Okay, got it.
The entire purpose of the compressor, like its sole engineering mandate, is to take a low-pressure gas, a vapor, and squeeze it into a high-pressure vapor. It is strictly 100% built to handle gas.
Just gas, nothing else.
Just gas. And that brings us to an unbreakable fundamental law of fluid dynamics. Gas is compressible. Liquid is inherently incompressible. You simply cannot squeeze a liquid into a smaller space.
So it's basically like what happens if you drive a normal car into a deep flooded street.
Oh, yeah, that's a great comparison.
Like the air intake sucks up water. Instead of air, it goes into the engine cylinders. The pistons try to fire and compress that water. And because the water won't compress, the engine just violently shatters itself. Hydrolock.
That is the exact same physics, hydrolock. In a normal, healthy chiller cycle, the liquid refrigerant absorbs heat from the building and boils off completely into a gas in the evaporator before it ever travels back to the compressor.
Right, so it's supposed to be completely vaporized.
Exactly. And we measure that safety margin with a metric called superheat. It essentially tells us how far past the boiling point the gas is, which guarantees there are no stray liquid droplets left over.
Okay, but what happens when things go wrong?
Well, when a chiller loses what we call superheat stability, which, by the way, can happen because of a slow leak altering the pressures, or maybe a stuck valve, or even just a really sudden change in the cooling load, that safety margin vanishes.
The buffer is just gone.
It's gone. And so liquid refrigerant actually manages to enter the compressor housing. Now, the massive mechanical screws or pistons inside that compressor, they don't know any better.
They're just doing their job.
Right. They are spinning at thousands of RPMs. They attempt to compress this incoming wave of liquid just like they would a gas. And the resulting hydraulic pressure spike is instantaneous and immense.
And because the liquid won't yield, the metal has to.
The metal violently yields. The internal suction valves, the discharge valves, the internal rotors, they are all subjected to massive hydraulic kinetic forces.
Wow.
They literally shatter instantly. Shrapnel flies through the internal casing. It is not a wear and tear issue where a bearing slowly grinds down over 6 months and you hear a little squeak.
Right, it's not gradual.
No, it is a catastrophic hard fault. The machine goes from perfectly functioning to completely destroyed in a fraction of a second.
Which honestly brings up the most glaring contradiction in this entire scenario. We are talking about industrial chillers that cost hundreds of thousands of dollars.
Oh yeah, massive capital investments.
Right. They are the backbone of data centers, pharmaceutical plants, hospitals, and they are absolutely covered in sensors.
Right.
So why does the machine shatter before a sensor can trigger an emergency shutdown?
That is the core question.
Like, if liquid is approaching the compressor, shouldn't a digital alarm just scream, "Abort! Liquid detected!" and cut the power?
You would think so, but that gap between the physical reality and the digital dashboard, that is the primary hidden structural bottleneck in modern industrial maintenance workflows.
Okay, break that down for me. Why is there a gap?
It all comes down to a concept called sensor latency. You see, the industry relies almost exclusively on external thermistors to monitor these temperatures.
External meaning they're on the outside of the machine.
Exactly. A thermistor is basically just a digital temperature sensor, but crucially, they are physically mounted to the outside of the heavy metal compressor casing. The structural flaw here is how heat actually moves through materials.
Because it's on the outside, it has to wait for the temperature change to literally travel through the metal wall of the machine before it can even take a reading.
You nailed it. We call that the thermal mass problem. An industrial compressor casing is a thick, heavy chunk of cast iron or steel. That introduces a severe time constant.
Because metal takes a while to cool down or heat up.
Exactly. Thermodynamics will always outpace mechanical conduction. Think about the physics of the liquid slugging event itself. The liquid enters the chamber. The physical pressure variances, like the actual kinetic act of the liquid hitting the rotors and the pressure spiking, that travels through the fluid at the speed of sound.
So it's basically instantaneous.
It's immediate. Heat transfer, on the other hand, travels at the sluggish, crawling speed of thermal conduction through inches of solid metal.
Man, so it's almost like touching a red-hot stove burner, but your nervous system is deadened and operating on like a 10-second delay.
That is a brutally accurate way to look at it.
By the time your brain finally receives the signal that says hot, your hand is already severely burned. The information is technically accurate, but it arrives entirely too late to be useful.
Right. The mechanical failure always precedes the digital alert. By the time that thick external metal casing cools down enough for the digital thermistor on the outside to register the anomalous temperature drop caused by the liquid inside,
It's already over.
it's completely over.
Yep.
The liquid has already been inside the chamber for several seconds. The valves are already shattered. The motor is destroyed. And this paints a really, really unsettling picture of how we operate high-stakes facilities.
Unsettling is an understatement.
We have these control room operators sitting in front of highly polished, incredibly complex modern dashboards. The UI is gorgeous. The dashboard looks completely optimistic. The lights are green. The temperatures look nominal.
But it's a lie.
It is lying because it is measuring the wrong physical property at the wrong speed. It's giving operators a profound false sense of security based on a delayed thermal echo of a catastrophic event that has, in physical reality, already occurred.
That is terrifying. You're staring at a green light on a screen, while 100 feet away, the machine is literally tearing itself apart from the inside.
Yeah, tearing itself apart.
And when we talk about these systems tearing themselves apart, we really can't just limit the conversation to a data center losing uptime or a facility manager paying some SLA penalty. The failure modes of heavy industrial equipment carry a much, much heavier weight.
They do. We have to zoom out and look at the actual human consequences here.
Let's do that. Because we need to analyze how hidden workflow gaps increase human safety risks in these high-stakes plant environments.
Right. The literature we were reviewing for this deep dive introduces a really fascinating engineering philosophy called restorative engineering.
Restorative engineering. What does that actually mean in practice?
Well, the core premise is basically a pushback against the whole Silicon Valley ethos of automating just for the sake of disruption or, purely cutting labor costs.
Right, like replacing people just to save a buck.
Exactly. The argument is that real, mature technology should be deployed to restore human capability, human dignity, and most critically, human safety.
Okay, that makes sense.
Yeah.
One of the authors in our source material actually tells a story that anchors this perfectly.
Oh, the grenade factory story.
Yes, that one. They talk about an experience early in their career observing factory workers who were manually handling and assembling actual explosive-like live grenades.
Which is just wildly stressful to even think about.
Right, and the author noticed how the workers moved. They were holding their breath, their shoulders were completely locked, the ambient tension in the room was just suffocating because one tiny slip meant a lethal kinetic event.
It's a constant life or death pressure.
Exactly. And the engineer who came in to automate that specific process, they didn't do it to save the company 30 cents per unit on labor costs.
No, the motivation was entirely different.
Right. They built a robotic process using highly precise 6-axis collaborative robots with built-in computer vision and AI specifically to remove the human being from the blast radius. They used automation to ensure that the worker got to go home safely at the end of their shift.
And that fundamental philosophy, removing humans from catastrophic risk, that maps directly onto industrial HVAC and refrigeration.
Even though it's not literally grenades.
Right. We might not be dealing with literal hand grenades in a basement mechanical room, but the stakes in high-level manufacturing are incredibly similar. The sources draw a direct line from that explosive assembly plant to modern pharmaceutical cold chains.
Oh, wow. Yeah.
They specifically highlight the massive biomedical manufacturing hubs in places like Hyderabad, India.
Places that are manufacturing life-saving oncology drugs, insulin, global vaccine supplies, the stuff people literally need to live.
Exactly. The output of a pharmaceutical cold chain relies on absolute, uncompromising thermal stability. We're talking about biomedical compounds that require continuous storage at extremely low temperatures, sometimes negative 70 degrees Celsius.
That's incredibly fragile.
It is. If you lose the cooling capacity, the molecular structure of the medicine literally degrades. You lose the product. So when thermodynamic destruction happens rapidly, when that primary chiller shatters its compressor because of a delayed sensor response to liquid slugging, it stops the cooling instantly.
And it's not just a broken machine anymore.
No, you aren't just facing a repair bill for a compressor. Entire production yields of critical medicine are ruined within hours. You are trading an unseen mechanical risk for a massive commercial catastrophe.
And when the product is critical medicine, a commercial failure directly impacts human health and survival on a global scale.
Exactly, which is why we need to categorize these mechanical failures differently.
Right, we tend to look at maintenance logs and just see, like error code 404 or compressor offline, and we treat them all as operational nuisances, just a line item on a spreadsheet.
But the severity scales wildly. The literature on vapor compression system failures categorizes these events by their impact on the facility and the workers, dividing them broadly into hard faults and soft faults.
Okay, let's break those down. What defines a hard fault?
Hard faults are total, sudden component failures. Liquid slugging shattering the internal valves, that is a hard fault. Another massive one is a motor winding burnout.
Which sounds intense.
It is. There was an industry study analyzing over 15,000 distinct HVAC failures, and they found that nearly 77% of hermetic air conditioning and refrigeration failures were actually electrical in nature.
Wait, 77%?
Yeah. Mostly, this means the motor windings burned out because the internal insulation deteriorated from operating at excessively high temperatures for way too long.
And a hard fault isn't a quiet event, right? It's a violent release of energy.
Extremely violent. If a high-voltage compressor motor burns out or a pressurized housing blows apart, you have a massive electrical arc or a spray of high-pressure refrigerant and metal shrapnel.
Which is terrifying if you're standing next to it.
Exactly. That is an immediate physical safety risk to the human technician who might be standing right next to that equipment in a confined mechanical room, just taking a routine gauge reading.
Man. Okay, so then on the other side of the spectrum, we have soft faults. And honestly, the name implies something minor, almost negligible. Like a soft fault is something you can just get to next quarter.
Right, it sounds harmless, but soft faults are the silent killers of industrial infrastructure. A soft fault is a slow-developing degradation of the system.
So the 11-week slow refrigerant leak from our data center example, that is a classic soft fault.
It is the textbook definition. Heat exchanger fouling is another really common.
Was that just dirt?
Yeah, that's when dirt and debris slowly build up on the outside of a condenser coil, or when microscopic layers of frost begin insulating an evaporator coil, which prevents the transfer of heat. It also includes slow internal mechanical blockages, like a filter dryer getting gunked up with acidic moisture over 2 years.
But if they're moving that slowly and they don't cause an explosion right away, why are they considered so dangerous? Why not just catch them during, like, an annual inspection?
Because they actively disguise themselves as normal operation. And if left completely unaddressed, a soft fault mathematically guarantees a hard fault.
Oh, wow. Okay, trace that causality for me. How does a slow leak turn into a hard fault?
Let's follow the physics. The system loses, say, 5% of its charge. The primary symptom is that it loses a little bit of cooling capacity. So the control system tells the compressor to run longer and harder to make up the difference.
Which means the compressor runs hotter.
Exactly. Now, the oil that lubricates the internal bearings of the compressor is actually carried through the system by the refrigerant itself. It travels in suspension.
Wait, so if you're leaking refrigerant,
You are also leaking oil, and the refrigerant that remains isn't moving fast enough to return the oil to the compressor. So now the bearings are running hotter, they're running longer, and they have less lubrication.
that is a recipe for disaster.
It is. Over months, this slow, silent, soft fault causes the bearings to literally seize, or the excess heat melts the insulation off the electrical windings, triggering the hard fault motor burnout. You ignored the soft fault, and it literally handed you a catastrophic kinetic failure.
Not to mention the environmental and regulatory disaster of just letting a machine bleed chemicals into the atmosphere for months.
The regulatory stakes are massive. Releasing hydrofluorocarbon refrigerants like R134A carries severe environmental consequences due to their high global warming potential.
Right, the EPA doesn't joke around with that stuff.
No, they don't. In the U.S., the EPA enforces strict regulations under Section 608 of the Clean Air Act. If you have an industrial system holding more than 50 pounds of refrigerant, and remember, these large chillers hold hundreds, sometimes thousands of pounds, and it leaks at an annualized rate exceeding 10%, you are legally required to repair that leak within 30 days of discovery.
And if you don't?
If you rely on reactive maintenance and don't catch that soft fault in time, or if you just fail to document the repair properly, you are facing EPA fines that can reach up to $44,000 per day per individual violation.
$44,000 a day. That is insane. I really want to ask you, the listener, to take a mental step back from the machinery for a second and think about your own workflow, your own operations.
It's a really important exercise.
Right, like what are the hard faults in your environment? What are the sudden catastrophic failures that you are currently treating as just unavoidable bad luck when they are actually the end result of a long ignored chain of events?
They're almost never just bad luck.
Exactly. And more importantly, what are your soft faults?
Yeah.
What are the tiny microscopic inefficiencies, the slow leaks that you are treating as purely operational nuisances, ignoring them while they slowly erode the structural integrity of your entire system?
It requires a pretty terrifying shift in perspective to realize that the small things aren't small, they are just early.
They're just early. Man, that is good. And that realization leads directly to the core financial paradox of this entire industry.
Right, the budget gravity.
Yeah, because if the human stakes are this severe, if the environmental fines are this punitive, And the mechanical destruction of a hard fault is this absolute. Why do massive, well-funded facilities still rely on reactive, manual maintenance? Like, why do they wait for the machine to break before they fix it?
That is the multi-million-dollar question.
Huh.
And the source material points to a profound organizational misunderstanding of what they call budget gravity. There's a massive chasm between what people think maintenance costs and what failure actually costs.
So let's contrast current manual maintenance costs with the budget required for full sensor integration. Let's do the autopsy on that 2.47 AM data center failure. What was the actual financial damage of that single night?
The granular breakdown of the costs in the postmortem report is just staggering.
Mm.
The root cause, again, was a
$1,800. I mean, for a facility that probably spends $20,000 a month just on landscaping, that is a literal rounding error.
It is nothing. But they didn't have predictive visibility. They relied on traditional delayed external sensors. They waited for the leak to physically drain the system until the pressure dropped so low that it tripped the mechanical safety switch at 2.47 AM.
And what was the bill for that?
Because of that latency, that $1,800 preventative fix ballooned into a $340,000 crisis.
Okay, wait. How do you even get to $340,000 from a single valve leak?
The cascade of consequences is brutal. First, the mechanical damage. Running severely low on charge likely caused the compressor to overheat or suffer liquid slugging as the expansion valve lost control. The compressor is destroyed. You are looking at $85,000 just in emergency mechanical repairs.
85 grand just for the hardware.
Hardware and labor. That includes the cost of the new compressor, emergency crane rentals to hoist it onto the roof, hazmat disposal of the contaminated oil, and expedited labor rates.
Oh.
Second, the operational loss. The primary chiller went down, forcing a computing capacity shutdown. That is calculated at $180,000 in direct lost revenue from the server, downtime alone.
Just brutal.
Third, the legal and contractual fallout. They breached their uptime guarantees with their clients, resulting in $45,000 in service level agreement, or SLA, penalties paid directly back to the customers.
So now you're literally paying your customers because your machine broke.
Right. And finally, the environmental cost. Venting that much R134A triggers regulatory scrutiny, leading to up to $50,000 in combined EPA fines, and the sheer material cost of buying virgin refrigerant to replace what was lost in the atmosphere.
From $1,800 to $340,000.
Yep.
That delta is the pure unfiltered cost of latency.
Yeah.
That is the tax you pay for not knowing what your machine is doing.
It's an ignorance tax.
So let's contrast that nightmare scenario with the actual physical budget required to drag a facility out of the dark ages. Let's map the specific hardware sensor data required to actually replace a guy walking around with a clipboard once a month. What does it realistically cost?
The required hardware budget to achieve full, continuous thermodynamic visibility is surprisingly targeted. It is not some massive infrastructure overhaul. It is an integration layer.
So we're just adding to what's there.
Exactly. To see inside the thermodynamic cycle, you need a very specific array of sensors on each chiller. You need high-precision pressure transducers on the suction and discharge lines. You need fast-acting immersion temperature sensors that actually sit inside the fluid flow, bypassing the thermal mass of the metal casing we talked about earlier.
Right, so you're actually measuring the fluid, not the pipe.
Yes. You also need current transformers clamped onto the electrical phases of the compressor motor to monitor power draw. You need ultrasonic flow meters on the water lines to measure the actual cooling load the building is demanding at any given second. And you need vibration monitors on the compressor bearings.
Okay, that sounds like a lot of highly specialized gear.
It is specialized, but the total procurement cost for this entire suite of industrial-grade sensors ranges from just $800 to $2,500 per chiller.
Wait, seriously? Only $2,000 for the entire nervous system?
That's it.
But I guess you still have to get that sensory data out of a concrete mechanical room in the basement and up into the cloud, right?
Right, that's the connectivity layer. You install localized gateways. These are devices that speak industrial protocols like BACnet or Modbus. These gateways aggregate all the raw electrical signals from the sensors, translate them into a unified digital format, and push them securely out to the network.
And the cost for those?
The hardware cost for those gateways is anywhere from $200 to $600.
Still incredibly cheap.
And finally, you have the analytical engine itself. the cloud-based AI platform that ingests, cleans, and runs the machine learning models on that continuous data stream. The SaaS subscription for that level of processing power is roughly $75 to $300 a month per machine.
Asymmetry here is maddening. I mean, a facility management board will sit in a conference room and agonize over a $3,000 upfront hardware expenditure and a $200 monthly software subscription.
They'll debate it for 6 months.
Yes. Meanwhile, they are passively accepting a risk profile where a single chiller going offline bleeds $25,000 a day in downtime or triggers a $340,000 catastrophic meltdown.
It is entirely irrational. The actuarial data on predictive maintenance proves the ROI is nearly immediate. The typical payback period for implementing AI-driven refrigerant monitoring on an industrial chiller is calculated at just 3 to 5 months.
That's incredibly fast for enterprise tech.
It really is. If the system prevents one single incident, like if it catches one slow leak and lets you do an $1,800 valve repair instead of buying a whole new compressor, the entire sensor network and software platform essentially pays for itself for the next decade. Massive longitudinal industry studies confirm that migrating from reactive to predictive maintenance delivers an average of 52% aggregate cost savings.
But throwing sensors at a machine doesn't magically fix the workflow, right? I mean, we've just spent the last 20 minutes establishing that waiting for a sensor to trip a threshold alarm is a fundamentally flawed strategy.
Right. The sensor is just the messenger.
So how does an AI platform actually treat this raw telemetry data differently than the old dashboard did?
It represents a total paradigm shift from static thresholds to continuous load-adjusted thermodynamic modeling. The workflow of the AI is entirely different. First, consider the resolution of the data. The IoT sensors are capturing the telemetry, the exact pressures, temperatures, amperage, and flow rates every 15 seconds. This is not a human technician walking by with a clipboard checking an analog gauge once every 30 days. This is high-resolution, continuous streaming.
Every 15 seconds. Over a month. That is millions of distinct data points for a single machine.
Millions. And traditional legacy control systems have no idea what to do with that volume of data. They simply look at a single metric, say discharge pressure. If the pressure goes above 250 psi, trigger an alarm. That's a static threshold.
A very dumb way to monitor a smart machine.
Exactly. The AI ignores static thresholds entirely. It takes the millions of data points and calculates highly complex dynamic metrics in real time. It calculates the exact superheat and subcooling down to the decimal point. It calculates the isentropic efficiency of the compressor. And crucially, it dynamically adjusts its expectations based on the external reality. It factors in the ambient weather outside because a chiller behaves very differently on a 90-degree day than a 60-degree day. It factors in the specific cooling load of the building at that exact moment. It even factors in the chronological age and wear of the equipment.
So it's contextualized the data, not just reading it in a vacuum.
Exactly. It synthesizes all those variables to build a unique thermodynamic fingerprint for that specific individual chiller. Once it establishes what perfectly normal looks like under any given load condition, it deploys pattern recognition.
Right, looking for anomalies.
Yeah, it compares the microscopic, subtle deviations in your chiller's performance against a vast cloud database of thousands of documented historical chiller failure cases from around the world. It looks for the statistical echoes of failures that have happened to other machines.
That's wild.
By leveraging this global data set, the AI models achieve a 94% accuracy rate in predicting leaks before they ever trigger a mechanical safety switch.
Okay, here's where I have to step in and play the skeptic for a minute, because this sounds almost too perfect.
Bring it on.
If the hardware is cheap, the return on investment is a documented mathematical certainty, and the AI is 94% accurate at predicting a leak. Why doesn't a facility manager just buy the software, crank the AI's detection sensitivity up to the absolute maximum, and just catch every single microfluctuation the second it happens? Protect the machine at all costs, right?
Well, that exact impulse, the desire to protect the machine at all costs by hypertuning the algorithm, leads us directly into what the source material from the Quiet Architect refers to as the post-automation choke point.
Post-automation choke point.
Yeah. It is the invisible operational wall you slam into right after you've successfully installed all the fancy new predictive technology. The choke point is the management of algorithmic sensitivity.
Explain algorithmic sensitivity in the context of this heavy machinery. What actually happens when it's dialed up too high?
Let's take our focus back to the pharmaceutical cold chain facility in Hyderabad. The system relies heavily on a component called the electronic expansion valve, or the EEV.
Okay, the EV.
The EEV is essentially a highly precise needle valve controlled by a digital stepper motor. Its entire job is to constantly open and close by fractions of a millimeter to meter the exact right amount of liquid refrigerant into the evaporator, responding to the changing heat load of the building.
So it's always moving.
Always. Because the heat load of a massive factory is always changing, the EEV is constantly hunting. It opens a tiny bit, overshoots, closes a tiny bit, finds equilibrium for a minute, then the load changes again and it moves again. This microscopic hunting is perfectly normal mechanical behavior.
But an AI looking at data every 15 seconds might view that hunting very, very differently.
Exactly. If you train your AI model to be hyper-aggressive, if you tell it to obsessively monitor the EEV and flag the tiniest microfluctuations in the stepper motor's positioning, you are inevitably going to generate false positives.
It's going to freak out over nothing.
Right. The AI will interpret a slightly erratic but totally normal load adjustment as an impending loss of superheat stability. It will think a liquid slugging event is seconds away.
And because it thinks the compressor is about to explode, it takes action.
It triggers an automated immediate system shutdown to protect the compressor from hydraulic destruction. Remember, the AI is doing exactly what you told it to do. Save the machine.
But zoom out to the commercial reality of a pharmaceutical plant.
Exactly. If you drop the cooling capacity unnecessarily for even 30 minutes, the internal temperature of the clean rooms spikes. The biomedical compounds degrade. You just ruined a multi-million-dollar medical batch.
Oh, man.
By turning the AI sensitivity up too high, you successfully traded a potential mechanical risk for a guaranteed commercial product loss. You brilliantly solved the engineering problem, but you created an absolute commercial catastrophe.
It is the exact same psychological dynamic as having a hypersensitive smoke detector in your kitchen that goes off every single time you use the toaster.
Oh, that is a perfect analogy.
If the alarm is too sensitive, it creates operational fatigue. It drives you completely crazy. And human nature takes over, right?
Mm-hmm.
We grab a broom handle, we smash the reset button, or we eventually just rip the battery out of the ceiling entirely just to get some peace and quiet.
Yep, we disable the very thing meant to protect us.
And then, when a real electrical fire starts in the walls at 3 in the morning, we are completely unprotected because we bypassed our own safety system.
That analogy plays out literally in industrial plants every single day. If an AI system generates false positives that shut down production lines and cost the company money, the human operators will lose trust in the algorithm immediately.
They'll just turn it off.
They will log into the control system and actively bypass the AI. They will mute the alerts. To prevent this human rejection, the AI cannot just be sensitive, it must be incredibly precise. It has to separate the true mathematical signal of an impending failure from the chaotic noise of normal daily operations.
So we need to define the signal. We need to detail the exact data triggers that confirm a machine failure is actually imminent. How does the algorithm know with absolute certainty that a failure is genuinely about to happen without crying wolf and ruining a batch of vaccines?
The sources outline very specific thermodynamic signatures that the AI is trained to isolate. These signatures provide weeks or even months of advance warning, completely subverting the old paradigm of reacting minutes before a crash.
Give me an example. Let's look at the telemetry of a developing refrigerant leak.
Okay, the AI does not wait for the overall system pressure to drop. That happens way too late. Instead, it closely monitors a metric called subcooling.
Subcooling.
Right. Subcooling measures how much the liquid refrigerant has cooled below its boiling point after leaving the condenser. If the condenser is slowly being starved of refrigerant because of a leak, the subcooling value will begin to drop.
But how much of a drop are we looking for?
If the AI detects that the subcooling metric is declining by exactly 0.2 degrees Fahrenheit per week on a consistent downward trend line, that is a highly specific, definitive signature of a volumetric leak.
0.2 degrees Fahrenheit over an entire week. That is microscopic. A human technician checking a pressure gauge with their own eyes would never, ever perceive a trend line that subtle.
It is humanly imperceptible. I mean, the ambient temperature of the room fluctuates more than that every 20 minutes.
Right. What else does it look for?
Another definitive trigger is the electrical current draw. As the system loses charge and efficiency drops, the compressor has to work incrementally harder to move the same amount of heat. If the AI detects that the energy consumption, the electrical amperage rises by 1.5% per month, completely independent of changes in the weather or the building load, It flags an anomaly.
But a single data point can still be noisy, right?
Yeah.
The real power has to be in combining them.
Exactly. The holy grail of predictive modeling is correlated parameters. Let's examine a compressor seal leak, which industry data suggests accounts for roughly 28 to 35% of these failure cases.
That's a huge chunk.
It is. When an internal seal degrades, high-pressure hot gas bypasses the compression chamber and leaks back into the low-pressure suction side. The compressor then has to recompress gas it already compressed, which compounds the heat exponentially.
That sounds incredibly inefficient.
It is. The AI detects the gradual decline in subcooling, but simultaneously it observes the discharge superheat metric climbing steadily. That specific combination, subcooling dropping while discharge superheat climbs, accompanied by very subtle, specific shifts in the internal pressure ratios and a marginal increase in compressor current draw, that is a distinct thermodynamic fingerprint.
So it's not guessing.
Not at all. The AI doesn't just say something is wrong. It tells the facility manager exactly what the problem is and exactly where it is located. And because it detects this pattern so early, this specific signature gives the facility 6 to 12 full weeks of advance warning before the heat degrades the motor windings.
6 to 12 weeks. That entirely changes the reality of the job. That is the difference between a panicked, screaming midnight meltdown with hazmat suits and a calmly planned Tuesday morning repair where you already have the replacement parts sitting on the loading dock.
It changes everything. Or consider a service valve leak, which represents another 18 to 25% of failure cases. The AI signature for this is different. It registers a steady overall thermodynamic efficiency loss, coupled with a consistent subcooling decline that actually correlates mathematically with the daily cyclical changes in ambient outdoor temperature.
Wow, so it factors in the weather affecting the leak.
Because the AI understands how the outdoor weather affects the leak rate, it isolates that signature. That specific pattern provides an astonishing 8 to 16 weeks of warning. By requiring these multivariable correlated thermodynamic triggers, the AI achieves its 94% accuracy rate without triggering the false positives that get algorithms unplugged.
All right, let's step back and look at the whole board.
Okay, let's do it.
The theoretical physics of liquid slugging and thermal mass are logically sound. The AI models and cloud architecture are proven. The specific hardware mapping of transducers and transformers is defined. The exact correlated data triggers are locked in.
Right, the tech is bulletproof.
But I can tell you right now, from practical experience, there is a massive human hurdle remaining.
Always is.
If you walk into a legacy manufacturing plant in Hyderabad or, a sprawling data center in California, and you tell a veteran facility manager with 30 years of hard-won experience that you want to plug a black box AI into his network that has the authority to shut down his primary chillers, he is going to laugh you out of the room.
Oh, absolutely. He'll throw you out.
Technical teams are inherently structurally resistant to new automated systems that introduce unknown variables into their operational stability. So, how do technical teams overcome resistance to automated monitoring systems? How do you bypass that deeply ingrained skepticism?
That skepticism is entirely justified. I mean, they have been burned by vendor promises before. This brings us to what I consider the most brilliant strategic methodology outlined in the source material. It is a concept the Quiet Architect defines as actionable validation, or more specifically, the 48-hour asymmetric bet.
The asymmetric bet, I love the framing of that. What makes it asymmetric in an industrial context?
An asymmetric bet is an action where the potential upside, the knowledge and operational savings gained is massive, but the downside operational risk is virtually zero.
Okay, I'm listening.
To convince a deeply skeptical engineering team, you completely abandon the traditional sales pitch. You do not ask them to install a new, untested AI gateway directly onto their live, mission-critical chillers.
Oh, so you don't even touch their live systems.
You do not touch the live production environment at all. You bypass their risk aversion by removing the risk entirely.
But if we aren't hooking sensors up to the live machines, how on earth do we prove the AI actually works on their specific equipment? We need to define a concrete 48-hour experiment to validate if predictive AI detects refrigerant leaks.
The methodology relies on historical forensics. You approach the facility manager and ask for 30 days of historical SCADA logs.
SCADA logs.
SCADA stands for Supervisory Control and Data Acquisition. It is the central nervous system of the plant that quietly records and archives every single temperature reading, pressure variance, and valve movement. It is the facility's historical memory.
Okay, so you just want their old data.
But you don't just ask for any data. You ask for the specific 30 days of logs from a chiller unit that has already suffered a documented catastrophic compressor failure due to liquid slugging.
An event that is already in their maintenance history.
Exactly. A machine they already know died.
So we're essentially performing a digital autopsy on a corpse they already buried.
Precisely. You extract those historical CSV files and you isolate two very specific granular data streams from the noise. The position logs of the electronic expansion valve, the EEV stepper motor, and the corresponding suction pressure data.
Just those two?
Just those two for this experiment. You then take the AI's core logic, specifically a lightweight, unsupervised clustering algorithm, and you run it exclusively on the data generated during the 48 hours immediately preceding the documented breakdown.
Wait, why restrict the algorithm to just the 48 hours before death? Why not feed it the whole month?
Because you are forcing the algorithm to prove its precision. The AI must independently identify the exact moment the machine's behavior transitioned from normal, healthy load hunting into fatal erraticism.
Oh, I see.
The success criteria for this experiment are brutal, binary, and absolute. The clustering algorithm maps the EEV movements onto a multidimensional scatter plot. Normal load changes form tight, predictable clusters of data points.
Right, nice and neat.
But as a system loses superheat stability and liquid begins to threaten the compressor, the EEV stepper motor begins to overcorrect wildly. It creates a highly specific, scattered oscillatory signature.
It panics, basically.
It does. The AI must retroactively flag these exact periods of EEV erraticism. It has to find the mathematical signature of expansion valve instability, the chaotic data cluster that occurs immediately prior to liquid suspension failure, and it must mathematically prove that this specific chaotic signature does not exist anywhere in the data during periods of normal operation.
That is an incredibly elegant way to circumvent the institutional veto. I mean, it costs practically nothing in computing power. It interrupts absolutely zero live workflows, so the plant manager has no valid operational reason to say no.
Not at all.
But think about the psychological impact of the result. If the AI can parse through a mountain of data from a Tuesday 3 months ago and say, look right here, at 4:08 p.m., exactly 48 hours before your compressor shattered, the EEV started microfluctuating in this exact mathematical pattern.
It's mind-blowing for them.
It definitively proves the 94% prediction accuracy claim using their own proprietary data. It proves to the most skeptical veteran engineer that the failure they previously wrote off as sudden, unpredictable, and invisible was actually highly legible and entirely preventable if they had only known where to look and possessed the computational power to see it.
It completely reframes the entire technological conversation. You are no longer selling them an abstract promise of future savings. You are showing them their own operational history through a new high-resolution lens.
Yeah, you're making the invisible visible.
You definitively prove the physical reality that thermodynamics outpace their old temperature sensors. And you prove that you can identify the structural bottleneck, the specific EEV stepper motor delays and subcooling drops days or weeks before the kinetic hydraulic forces actually shatter the steel valves.
Let's synthesize the journey we've just been on, because the scale of this problem is massive. We started by looking inside the physics of a vapor compression cycle, understanding that an industrial compressor is strictly a gas machine, and that liquid slugging will cause instantaneous, catastrophic hydraulic destruction.
Complete devastation.
Right. We realized that our entire industry's reliance on external temperature sensors is a fatal structural bottleneck, because the thermal mass of a compressor casing introduces a time constant that is simply too slow.
The machine physically breaks before the external sensor even feels a change in temperature.
And from there, we saw the solution. By mapping a specific, targeted array of hardware pressure transducers, current transformers, immersion sensors, and feeding that high-resolution telemetry into a cloud platform every 15 seconds, we bypass the thermal mass problem entirely. We build a dynamic, continuous thermodynamic model, the Ziller.
A model that doesn't just wait for a dumb static pressure switch to trip at 2:47 a.m. It looks for the microscopic, correlated data triggers. The 0.2 degrees subcooling decline coupled with climbing discharge superheat.
Which is huge. And it meticulously manages its own algorithmic sensitivity to avoid crying wolf and shutting down the plant for false positives, which is the only way to protect those incredibly fragile, life-saving pharmaceutical yields in manufacturing hubs like Hyderabad.
You have to protect the human element.
Always. And finally, we explored how to cut through the institutional red tape and prove all of this without risking a single live system by executing a 48-hour asymmetric bet on historical SCADA logs. We bypass flawed legacy sensors, we overcome deeply entrenched human resistance, and ultimately, we protect both massive operational budgets and fragile human lives from the violent kinetic reality of hard faults.
Which really brings us to a final lingering concept drawn from the fault detection and diagnosis frameworks we've been analyzing today.
Lay it on me.
We have talked extensively today about how, in the realm of massive industrial systems, the most dangerous and expensive failures are almost never the sudden explosions.
Right.
The worst failures are the soft faults. Problems like a microscopic refrigerant leak or a slowly fouling condenser coil, an issue that hides quietly in the background for months. It actively disguises itself as normal operation.
While the dashboard is bright green.
Exactly. But slowly, silently, that soft fault degrades the integrity of the system. It steadily wears down the margins of safety, just waiting patiently for the hottest, most stressful day of the year to trigger a catastrophic, irreversible hard fault.
The silent killers that we ignore because they don't demand our immediate attention.
Exactly. So as we wrap up, I want to ask you to pull your focus away from industrial chillers and heavy manufacturing for a moment. Look at your own life. Look at the team you manage, the business you were building, or the relationships you maintain.
Oh, wow.
What is your most expensive soft fault? What critical process, what structural bottleneck, or what unsaid grievance is slowly leaking right now, perfectly disguised as normal daily operation, just waiting for the hottest, most stressful day of the year to completely shatter your system?
Man, that is a deeply uncomfortable question. And honestly, it is a topic worth a deep dive all on its own.